Hello everyone, welcome to CS350. This is Karthik Gopalan. In this lecture we will learn about redundant array of inexpensive disks, or the RAID technology. The RAID technology allows you to construct highly reliable and high throughput storage systems using very inexpensive disks. Let's first start by looking at the one of the earliest hard disks that was manufactured by IBM for its mainframe computers. As you can see, this is a really large hard disk with very limited capacity and reasonable access times for that time, 1956. So again, these disks used to be very expensive, and because they were expensive, they were also built to be more reliable, so that they could be used for a long time by a large number of users. So as computing technology evolved over the decades, people had a desire to move away from large mainframe computers to personal computers. This meant that the form factor for hard disks had to shrink to fit into a personal computer. Thus, disk manufacturers improved the technology to make disks cheaper, and also to increase the capacity of the hard disk to hold more data. However, one of the side effects of shrinking the form factor and making the disk cheaper was that the reliability of the disk suffered, which meant that you no longer um, uh, could use the same disk for a long time without failure. So also the original IBM mainframe hard disks were very large, and consequently they had significantly large capacity to accommodate a large number of users. However, for desktop computers, individual users didn't need as much capacity. So on one end of the spectrum, you had very large, expensive disks, which were very reliable, and on the other end of the spectrum, you had smaller, cheap disks, which were not very reliable. So at the end of the 1980s, researchers wanted to see if they could put together multiple cheap hard drives and get the equivalent capacity of a large, expensive hard drive. So in theory, you could always write a software that could span data across multiple hard drives. The only problem with doing so was that you lost reliability compared to even a small hard drive. So to understand the reliability problem, let's look at a metric called mean time to failure. Hardware manufacturers use this term mean time to failure, or MTTF, to measure what is the average life of a particular hardware component. So for example, if you buy a hard drive and look at the MTTF metric, it will tell you how many hours a typical hard drive can be used before it is expected to fail. So hardware manufacturers have various ways of measuring the MTTF, and this is an important consideration for administrators who buy large system components. So if you consider a MTTF of a disk drive as say 30,000 hours, meaning that on the average, if you use the disk drive for 30,000 hours, then it will be expected to fail. Then if you buy n such hard drives, then the mean time to failure for the entire set of hard drives reduces by a factor of n. So for the entire set of n drives, the mean time to failure will be 30,000 by n. In concrete numbers, if you bought 100 hard drives, then the mean time to failure would be one failure every 300 hours. So, or if n was 10, then the mean time to failure would be every 3,000 hours. So obviously we don't want to compromise on reliability as we construct a RAID array. That is, we are putting together multiple inexpensive disks to construct a larger capacity virtual disk. So that was the original motivation to increase the capacity using several cheap hard drives. But today, you can go out on the market and buy a really high capacity hard drive for a reasonable price. So, for example, you can buy several terabytes worth of hard drive for a few $100s. So, so neither capacity nor cost are major concerns today. However, RAID arrays still have an important purpose. The most important purpose is that if you put together multiple hard drives, then you can get a large amount of throughput. So you can do so by performing I/O operations in parallel on several disks at the same time. So as a result, uh, you increase disk throughput is a big gain when you put several disks together. The other benefit of RAID array is that you eliminate the need to make backups. Obviously, if you have a large capacity hard drive, then doing a full backup of the entire drive to another drive will take a very long time. Anyone who has tried making a full backup of 1 terabyte or 2 terabyte disk knows that it can take like up to half a day or a day depending on the speed of your computer. So disks today are too big to be backed up efficiently, and for large enterprises they want instant reliability, and RAID technology provides this instant reliability. So today the primary reasons for using RAID are to increase the throughput and to achieve instant reliability of data. So before we delve into the specifics of the RAID technology, it's important to understand what we mean by storage virtualization. We all learned about the concept of block devices earlier in this course. So if you look at the viewpoint of a file system, the file system stores data and metadata, and it interacts with the storage device through a block device interface. A block device interface can be thought of as a linear array of data blocks starting from 0 to maximum. So any partition on a disk, for example, it could be considered as a block device, and the file system will view it as a large array of blocks. Each block is of a fixed size, say 4 kilobytes or 8 kilobytes, however you configure it to be. Underneath the block device, however, there is a device driver that manages the physical device. So if you had only a single disk, then the device driver would be talking to the single disk or the disk controller of the single disk. On the other hand, you could also replace a single disk with several storage devices, or in the case of RAID array, you can replace it with several disks. And this is shown in this picture by the three smaller rectangles at the bottom of the figure. So if you put together several disks and there is a device driver in the operating system that exports multiple disks as a single block device, then you perform what's known as disk virtualization. So essentially the file system thinks that it is reading and writing to a single block device, but underneath that block device may be mapped to multiple physical disks. So there's a software or firmware based mapping that maps the logical IO space to physical IO space. So in this picture, we show that there are several levels of RAID technology, from RAID 0 all the way to RAID 5, and not shown in this picture, but you also have RAID 6 and RAID 10. Each of these levels gives you different levels of throughput and reliability, and also different amounts of space overhead. So we will discuss the specifics of each of these RAID levels. But the thing to note here is that the blue disks here represent the data disks where actual data is stored, and the gray disks represent the parity disks or where additional redundancy related information is stored. And sometimes, as in the case of RAID 5, the redundancy information may be interleaved with the data itself. So let's start with RAID 0, which is the simplest form of RAID technology. In RAID 0, you do not get any redundancy, which means there is no protection from any disk failure. So instead we are focused on achieving high throughput. So if you have n disks, then the way RAID 0 works is that you take all your data blocks of a block device and you stripe them across multiple disks. So as shown in the figure, block 0 will go on disk 0, block 1 of the partition would go on disk 1, block 2 on disk 2, block 3 on disk 3. And when we reach disk 3, we wrap around and start with disk 0 again. So block 4 goes on disk 0, block 5 on disk 1, and so on. So essentially you are taking all your data blocks and spreading them across all the disks in the disk array. So as a result, you can perform I/O operations on 4 disks at a time. In this example, if you had n disks, then you can perform I/O operations on n disks at a time. So these I/O operations could be either reads or writes. So as a result, you get very high throughput, very high parallel throughput, but there is no fault tolerance. In fact, actually, uh, the reliability of a RAID 0 array is worse than that of a single disk, as we had discussed in the beginning of this lecture. So to improve the reliability, we go to RAID 1. RAID 1 keeps an identical copy of every data block. What that means is that if you have a data block stored in a disk, then there will be a mirror image of the data block stored in another disk. So disk 0, so let's say block 0 is stored on disk 0, then a copy of block 0 will be stored on another disk. Here we call it mirror 0. And then block 1 on disk 1, there is a copy of block 1 on mirror 1. So, so uh, uh, such a technology is very simple to implement. All you need to do is keep duplicate copies of every data block, and it gives you reasonably good fault tolerance. As long as a single disk fails, you're guaranteed that the data can be recovered. If a disk and its mirror disk fail, then you are no longer able to recover the data. However, if let's say that the primary disk fails and a mirror disk of uh, another data disk fails, you'll still be able to recover the data. So the only failure condition that from which RAID 1 cannot recover is if both the primary and the mirror disks fail. So as a result, RAID 1 guarantees protection from all single disk failures and from most two disk failures. However, a big disadvantage of RAID 1 is that you have to set aside half of your disk capacity to store duplicate information. Subsequent RAID levels try to reduce the amount of overhead required to store redundant data. So in RAID 2, we assume that the disks are unable to perform any error detection. What this means is that if some data on a disk is corrupted, then the disk controller is not able to tell. So we have to have software level mechanisms or firmware level mechanisms to detect the corruption of data or to detect the failure of a disk and to fix it. So we have to perform error detection and correction. Many years ago, disk technologies uh, did not have built-in error detection. So as a result, RAID 2 focused on providing both error detection and error correction. So, so in this picture, we have three disks, disk 0, 1 and 2, and two parity disks, disk parity 1 and parity 2. So disk 0, we stripe data blocks across disks 0, 1 and 2, as in block 0, 1, block 0, block 1 and block 2. Parity 1 and parity 2 disks hold some additional information, which is basically a parity operation, parity bits computed as a function of data blocks 0, 1 and 2. Similarly, uh, for blocks 3, 4 and 5, the corresponding parity information is stored in, in the disks parity 1 and parity 2. So the specific um, type of the parity information or the parity function Depends on what type of error detection and correction you are performing. So depending upon the type of the function f, you might have different amounts of overhead for the parity information. RAID 2 is no longer relevant because most of the modern disks have built-in error detection. If a disk block fails or becomes corrupted, internally the disk controller is able to detect such data corruption and map the bad block to a new data block. If on the other hand the disk fails irreparably, that is, you are no longer able to access the data, then the disk controller is able to signal to the operating system that the entire disk has failed. So now we have a technology where disks are expected to signal to the operating system when they fail. So we deal with the failure of the entire disk, or the whole disk continues to operate correctly. Hence, modern RAID systems only have to deal with error correction. They don't have to deal with error detection. For error detection, we rely upon built-in hardware in the disk controllers. So before we consider RAID 3 and higher levels, let's start with a primer on the XOR operation. XOR is a logical operation whose truth table is given in this slide. If you XOR bits 0 and 0, you get a 0. If you XOR bits 0 and 1, you get a 1. 1 and 0 gives you 1. 1 and 1 gives you a 0. So what this means is if the two bits are the same, then the result is a 0. If the two bits are different, the result is a 1. XOR is both associative and commutative. So which means associative means that you can apply the XOR operation to multiple bits, and any pairing of the bits would give you the same result. Commutative means that you can take uh, any of the bits to the other side of the equation and the equation would still hold. So one interesting property of XOR from the viewpoint of RAID systems is that if you lose any of these bits of data, then you can recover it by using the commutativity property. So for example, if you lost a bit and let's say the other piece of information is 1 and the parity information, that is the XORed result, was 0, then you can recover the lost bit by taking 1 to the right hand side. So 1 XORed 0 would give you 1, and 1, so hence 1 was the lost bit. So essentially you can recover a lost bit by using the commutative property. This property also extends to any arbitrary number of bits. So in the next example, if you had 1 XOR lost bit XOR 1, which is equal to 0, then you can recover the lost bit by doing an XOR of the remaining information. So 1 XOR 1 XOR 0 equals 0. So the 0 is the lost bit. So you can experiment with various combinations to see whether you can recover the lost data, just to convince yourself that XOR does indeed help. So so keep in mind that this means that you can only lose one piece of information. If you lose more than two or more pieces of information, then you can no longer recover the data. So using XOR as parity information is helpful for to recover from single disk failures. If you have two disk failures, then certainly you cannot use XOR anymore. So let's start with RAID 3 and see how we can apply this principle. In RAID 3 you have n data disks and one parity disk. So this additional parity disk is used to store extra information for redundancy. So if you're given a block bk of data, so the first thing we do is we divide up the block bk into n fragments, b1 through bk1 to bkn. So each of these fragments is stored on a separate disk. So as shown in the figure, if we take block 0 and divide it into three fragments, block 0, 1, 0, 2 and 0, 3, then we take an XOR of these three blocks, compute parity 0 and store parity 0 in the parity disk. Similarly, three fragments of block 1 are stored across the three disks, and the corresponding parity information is stored on the parity disks. So what happens in a failure? Let's say any of these four disks in the figure fail, any one of the four disks. So you can reconstruct the lost disk by performing an XOR of the data in the remaining disks. So that's what is shown in the formula in this slide. So the advantage of RAID 3 is that it's very simple to implement. The firmware or software has to deal with only one block at a time. When you receive a block for writing, you break it up into fragments, compute the parity, then write the fragments to data disk and the parity to the parity disk. And when you want to read a data block, you would simply read the fragments from the corresponding data disk, put them together, and return to the user. So, um, although it's simple to implement, the disadvantage is that you can only do one I/O operation at the time. Let's say you want to read or write a particular block. You have to involve all the data disks and the parity disk. So there is no parallelism in I/O operations. You cannot issue multiple reads or write requests at the same time. So RAID 3 gives you redundancy at a reasonably low overhead, but it does not give you any parallelism in I/O operation. Any parallelism is within a single block, not across several blocks. So the other option is to go to RAID 4. In RAID 4, we try to improve the parallelism provided by RAID 3. As with RAID 3, we have n plus 1 disks, that is n data disks and 1 parity disks. However, the job of the firmware or the software is a little bit more complicated. So instead of fragmenting a data block across multiple disks, we keep the block intact. Each block is stored in a single disk. So in this example, block 0 is stored on disk 0, block 1 on disk 1, block 2 on disk 2, and then block 3 on disk 0 again, and so on. So this is similar to the way we were doing striping in RAID 0 and RAID 1. So the only difference between RAID 3 and RAID 4 is that now we compute parity across all the blocks at the same level. So in RAID 3 we were doing parity computation across fragments of a block. In RAID 4 we do parity computation across entire block, across distinct blocks. So parity 0 in this example is a parity of blocks 0, 1 and 2. Parity 1 is a parity of blocks 3, 4 and 5, and so on. So again, as with RAID 3, if you lose a disk, then you can recompute the parity, you can recompute the lost data by XORing the remaining disks. The advantage of RAID 4 is that now you can do multiple read operations simultaneously. So if you were reading, say, block 0, block 4 and block 11, then you can exercise disk 0, disk 1 and disk 2 in parallel. So you can do 3 I/O operations at a time in this figure. Or if you had n data disks, then you can do n read operations at a time. However, for write operations, we run into a problem. If let's say that you write to a data block, you also have to update the corresponding parity information. So not only do you have to update the data disk, but you also have to update the parity disk. But we have only one parity disk. So as a result, even if you are writing data blocks to two different data disks, the parity disk becomes a bottleneck. The parity data information has to be committed to this same disk. As a result, you do not have write parallelism. A write operation cannot complete until the parity information has been written to the parity disk. So, you can have uh, read parallelism of up to n, but you can only perform one write operation at a time because of bottleneck in the parity disk. So it's fairly straightforward to overcome the parity disk bottleneck. So in RAID 5, instead of having a single parity disk, we spread out the parity information across all the disks. So what that means is that again we have 4 disks as in the previous figure, but there is no dedicated parity disk. So the parity information for blocks 0, 1 and 2 is stored in disk 3. Parity information for blocks 3, 4 and 5 is stored in disk 2, and so on. So essentially we stagger the parity information for different rows across different disks. As a result, now we get a little bit more parallelism. In this example, you could be writing to block 0 and say block 4 at the same time. Then you would, for to write to block 0, you would update disk 0 and disk 3 where the parity information is stored. And to write to block 4, you would update disk 1 and disk 2. So as a result, you can have up to n by 2 parallel write IO operations going on simultaneously. So you can have a maximum parallelism of n reads and n by 2 writes at any time. So there is one small detail that we overlooked in our previous discussion of write operations. When we perform a write operation, we have to recompute the parity, right? So every time you update a data block, the parity must be updated as well. But how do you recompute the parity? So in this picture, you have n blocks, n data blocks, all of which contribute to the parity. So if you were to do it the naive way, then you to recompute the parity, let's say you are writing to a block, then you would have to first read all the n minus 1 other blocks in the stripe. Then you have to perform an XOR of all the data blocks. Then you get the new parity information. So to perform a single write, you would have to perform n minus 1 reads of n minus 1 other data blocks, and then you would have to do 2 writes, one for the new data block and the other for the new parity block. Needless to say, this is really expensive. We don't want to be doing n minus 1 reads just to perform a single write. So is there a better way? It turns out that in fact you can use the property of XOR to 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 simplify the process of recomputing parity. So so remember that we have two values of parity, the old value of the parity and the new value of the parity. The old value of the parity can be used to figure out the collective XOR value of all the n minus 1 blocks. So for example, if you take the XOR of old value of the data block that's being written and the old value of the parity, then that together gives you the XOR of the data value in the remaining blocks. So that can be XORed with the new value of the data block to give you the new parity information. So as a result, all you need to do is need to know is the old value of the data block you're writing, the old parity value, and the new value of the data block you're writing. XOR these three pieces of information and you get the new parity. So as a result, you only need to perform 2 reads and 2 writes. So 2 reads because you want to fetch the old data block value and the old parity value, and 2 writes because you want to write the new block value and the new parity value. In fact, you don't even have to perform 2 reads in many cases. Oftentimes, the old value of the data block is already in the file system cache. As a result, you only need to read the old value of the parity from the disk, from the parity disk. So as a result, you can reduce the number of IO operations to 1 read and 2 writes. So let's take a quick look at the various ways in which different RAID levels compare against each other. So with RAID 0 and RAID 1, we are assuming we have n disks. With RAID 2, 3, 4, and 5, we are assuming we have n plus 1 disks. So in terms of fault tolerance, RAID 0 doesn't offer any fault tolerance. RAID 1 protects you against all single disk failures and most two disk failures. The only failure it doesn't protect you against is if both the primary and the secondary disks, primary and the mirror disks fail at the same time. RAID 2 through RAID 5 protect you only against a single disk failure. In terms of parallelism, IO parallelism, with RAID 0 you can perform n read operations at a time and n write operations in parallel. With RAID 1, note that for read operations, you can read from either the primary disk or the mirror disk. So as a result, you can in fact perform n read operations in parallel. But for writing, you have to write to the primary disk and the mirror disk. So you can only perform n by 2 write operations in parallel. With RAID 2, you can perform n read operations at a time, but only one write operation at a time, since parity disks are dedicated. With RAID 3, you can perform only one read or one write operation at a time because each block is fragmented across several disks. With RAID 4, you can perform n reads at a time, but you can only perform one write operation at a time because the parity disk is a bottleneck for write operations. With RAID 5, you can perform n plus 1 read operations at a time because there's no longer a dedicated parity disk. But as far as write operations are concerned, you can only perform n plus 1 by 2 write operations at any time. So as you can see, there are various degrees of read and write parallelism across different RAID levels. In terms of space overhead, RAID 0 has 0% space overhead to store parity information. RAID 1 has 100% overhead. For every data disk, you need a parity disk. For RAID 2 through RAID 5, we need additional parity in disks. So in RAID 2, if you have k parity disks, then the overhead is k by n times 100. For RAID 3, 4, and 5, you have one additional parity disk. In RAID 5, the parity information is distributed across all disks, but it's equivalent to having a single parity disk. So in all these cases, you have 1 by n times 100% overhead. So this brings us to the end of the RAID lecture. So in summary, we saw that the original purpose of RAID was to take advantage of cheap commodity drives that had small capacities individually, but when put together, they could give you a large capacity disk. On the other hand, since disks are now both cheap and have large capacities these days, so now the main purpose of using RAID is to have high throughput and to have instant reliability to protect against disk failure. So if you have a small installation, then RAID 1 is a very attractive option. Otherwise, you can either use RAID 3 for simplicity or RAID 5 for higher degree of parallelism. Note that uh, dis all of these levels that we discussed, protect you, they guarantee protection against only a single disk failure. So if you want higher guarantees like guaranteed protection against two disk failure, then you may have to consider higher levels of RAID such as RAID 6 or RAID 10.